Hello and welcome back. Now we're going to be talking about curve evolution. This is the concept that is going to bring us to the understanding of active contours, as we have seen in the previous week and as we have talked in the previous videos as well. So what is curve evolution? Very simple concept. The basic idea is that, as we see here, we have a curve, and at every point we have a velocity that defines how that curve is moving. And that's represented by this equation. So it's a partial differential equation. If I'm going to write it in explicit form, it's going to say that the derivative of the curve, remember, the curve is parameterized by a parameter p. The derivative of the curve in time. So the curve is changing in time is equal to certain velocity, and the velocity is again at a given point, and the velocity might be changing in time. So this is the complete equation. It's a partial differential equation, and we write in shorter form, as here we know that the subscripts represent derivatives. So at every point we're moving the curve. So at some time we're going to have this curve. A bit later we might have a curve like here, and then a bit later we might have maybe a curve like this, depending on the velocity at every single point. And as we are going to see, these type of deformations of curves, remember, curves are boundaries of shapes. These type of deformations will bring us some very interesting movements inside images and inside videos. So let us see a few properties of this and also a few examples that will illustrate the importance of this concept. The first important property is the following. We have a velocity. At every point, that's a deformation velocity. Now, that velocity can be decomposed, of course, into the component that is normal to the curve, perpendicular to the curve. We have defined normals and tangents. So we have a vector, we decompose it into its normal and tangent components. It turns out that this tangent component does not change the shape of the curve. So it's not relevant. So that's written here. This is the general equation that we have, but we basically project the velocity towards the normal direction, and we take only that projection and we move in the normal direction. So basically, from the geometric point of view, the most general deformation is a deformation in the normal direction to the curve. You can add velocities in the tangential direction. They just don't change the shape. Remember, the tangent is the velocity you're traveling the curve. So adding these terms is kind of changing the velocity that things are moving, but they're moving along the curve. They're not really deforming the shape of the curve. So often we are going to just write curve evolution as deformations in the normal direction. That's all what we care. Sometimes, for convenience, if you want, you can add tangential components. You can add them as you wish to add them because they don't deform the curve. For example, if I have a motion like this, ct equal some function in the tangent direction, so no normal component, this does not change the shape of the curve at all. It's only like making a lot of effort around the curve, but not changing the curve at all. So the general deformations are in the normal direction. Let's just talk a bit more about that, and let's just see a few examples. By the way, this property is not very hard to prove, and you can do that as an exercise if you wish to do so. So the first one that we want to talk is what's called curvature motion. So the deformation in the normal direction is proportional to the curvature at that point. Before I tell you what basically that type of deformation is doing to the curve, let's just look a bit more. Remember that the second derivative of the curve, when we take the derivative with respect to the Euclidean arc length, is this. So the second derivative of the curve we know is a vector perpendicular to the curve, and the magnitude of that vector is the curvature. So this deformation is like the first derivative in time equal second derivative according to arc length. For those that are familiar a bit more with differential equations, this is like what's called the heat flow, but it's very geometric because of this arc length. So in explicit form, this says that dc dt is equal to the second derivative of c according to the arc length. Okay? It's a very interesting deformation of curves, and what it does, it basically, first of all, is Euclidean invariant. Curvature is Euclidean invariant, meaning it's invariant to rotations and translations, and the normal is also Euclidean invariant. So if you do a rotation and translation or an Euclidean transform, and first you do the deformation and you do the deformation here, also here, along the way of the deformation, the curves are related by exactly the same rotation and translation. So you start from a curve, you rotate it, you start deforming both according to this motion. At any time you stop, the same rotation and translation relates the deformed curve. That will happen as long as you use properties which are invariant to rotation and translation. Now this motion does some very beautiful things to curves. The basic idea, and this has been proven a number of times, but was first proved by Grayson some time ago, that you take any curve, think about any curve that is not self-intersecting. So that's called a simple curve. That's actually the boundary of a shape. You take any curve, you deform with this, and the curve becomes convex. It just opens up. It just gets very smoothly into a convex shape. Once it's convex, if you keep going, it starts rounding. And basically, it ends in what's called a round point. So it actually will vanish. It will keep shrinking. Basically, it will keep going inside proportional to the curvature. And at the end, it will look like a round point. So if you dilate it all the time, if you just make the area constant all the time, you will see that it's becoming round and round. So what you see is that no matter how crazy and how difficult your shape is, as long as it doesn't self-intersect, and basically it just opens up, so it's becoming smoother and smoother until it becomes a circle. Remember, the circle has constant curvature. So this is basically going from a very crazy curve. It might be a curve that does a lot like this, as much as you want, and then smoothly it's becoming just nicer. So it's actually regularizing the curve, and if you wait all the way, it becomes round. Constant curvature. If you remember, the heat flow takes heat, no matter the distribution of the heat, at the end becomes constant in the room. This, no matter what the curvature is all around, at the end it becomes constant. It becomes 1 over the radius. How much it takes it to get to here? We're going to know that in a couple of minutes. Don't worry, this is a very simple property to prove how long it takes for the curve to completely collapse into this round point. Before we do that, let's do a couple of additional examples. Now, that was the Euclidean case. What about the affine case? The affine case turns out to be this function. This is the Euclidean curvature. Where do we get it from? We're going to do, let me just write it here for a second. We're going to do the same as we did before, but now according to the affine arc length. Now remember, when you take second derivative according to the affine arc length, you are not necessarily perpendicular to your curve. But we know that the tangential component does not matter, so you have to project it. And we already saw before in one of the previous videos that the projection of the affine normal, the second derivative, into the Euclidean normal is kappa to the 1/3, is the curvature to the 1/3. So these two equations are, from the geometric point of view, equivalent. They're absolutely the same equations, but this has motion in the tangent direction that is not relevant. So once we project it to the normal direction, we get this beautiful equation. Looks like Euclidean, but has this magic exponent that makes it affine invariant. That means that if I take a shape and I do an affine transform of that shape, and now I evolve both of them, then all the time I can relate them by exactly the same affine transform. So this is affine invariant. So I can be doing smoothing in affine regularization, cleaning my curve in an affine invariant fashion, meaning invariant to tilts of the camera when we are under the assumptions that the affine model is a good model, as we discussed before. And now you can also prove a number of interesting properties. Similarly to the Euclidean case, what happens here is that the curve, no matter how crazy it is, it becomes convex again, and then it goes into an ellipse. It doesn't go into a circle. We are in a affine domain. Circles and ellipses are the same in the affine domain because a circle with an affine transform goes into an ellipse. Moreover, the ellipse has constant affine curvature. Remember this mu that we discussed, that is the affine curvature. So as in the Euclidean case, we start from something that might have a crazy affine curvature. Slowly, this crazy or this very changing affine curvature is deforming towards a constant affine curvature. And that's why this is called the affine heat flow. It's taking curvature that is very non-uniform and is making it uniform at the end. So that's another very interesting motion. The Euclidean and the affine, they're both kind of cleaning the curves, meaning cleaning the shapes. Now, not every motion does that. If we take the simplest of the motions, constant speed in the normal direction, just at every point, move a step. I don't care about the curvature of my curve, I just move a step at every single point. Now, this is a very important equation. It's the equation that creates offsets. You're creating a curve which is parallel to the previous curve. You can move inwards or you could put minus here and move outwards. So you're creating another curve that is parallel. It's equal distance all the time. And basically, if you keep going, you get another equal distance, and then you get another equal distance here, and so on, depending how far you go. Remember, this is a differential equation in time. You can stop or you can keep going. Now, this curve is obtained by doing this deformation, but it's also obtained in the following fashion. You basically draw a circle, center on the curve, and with a given radius. And then for every point, you draw a circle with exactly the same radius, and then you take the envelope of that circle, and that gives you this constant motion deformation. And that's related to what's called the Huygens principle in physics. That's how waves propagate, basically when they don't have obstructions. So if you had, maybe you did these experiments in physics where you basically propagate waves, and that's what this constant motion does, or the Huygens principle. So maybe you knew that so this is a wave, and maybe you knew the Huygens principle basically is the one that governs the motion of the waves without any obstructions. So that's just nothing else than this type of curve evolution. So this curve evolution is important in image processing, but it also explains a lot of very interesting physical phenomena. Constant motion. Now, this constant motion is very interesting. For example, it can actually change the topology of a curve. If you start from this curve, and then you move with constant velocity, after a while, the curve splits in two. This cannot happen in the curvature motion for Euclidean or affine that we saw. The curve stays simple, stays smooth. Here, actually, it can split into pieces. It's like the waves can split into pieces. There are even more things happening. If you start with a smooth curve and you move inwards, after a while, these sides will collapse. They don't have a curvature term here. So they don't have any way to understand that the curvature is becoming very, very high. It's going to collapse. It's going to get to a corner. Corner has infinite curvature. Just you really turn very fast. Doesn't know because there is no curvature term here. So after some time, it will basically collapse and it will create what are called shocks. And we know that from waves. When waves are coming, they can collapse and they can create these shocks. This doesn't happen with curvature motions for the affine or Euclidean case. The curve stays smooth all the time. It will never collapse. The constant flow creates this collapse. So we have the both extremes. The constant flow can change topology, can collapse things, can create corners. Now, the curvature regularizes, this create corners. So maybe it sharpens shapes. So we have both motions depending on what we want to do in the image processing arena. Now, once we have this type of curvature motions, and I'm basically gonna write them here again so you remember them, we have the constant flow, no speed here or speed equal 1, the curvature flow Euclidean, and the affine flow. The constant motion can split curves, can do shocks, can do corners. The Euclidean one regularizes everything into a circle, and the affine regularizes everything into an ellipse. Which ellipse? We don't know. We are in a affine space. All ellipses are the same. Now, we can write a lot of properties of this deformation, and those are just interesting curiosities. Sometimes they're very useful for image processing, sometimes they're just nice things. One of the things we're going to see is when does this curve in the Euclidean case collapses. And this is just some calculus, so it's not very hard to do. But if you take a certain deformation, so remember we only consider the normal deformation and with velocity, with speed v. So for example, how is the length changing? I'm deforming a curve. What's happening to the length of the curve? So we have to take the derivative of the length, and this is the definition of the length of curve. So the integral all around the curve, that's the symbol with the circle there, says you go all around the curve. We're talking about closed curves in this case. So you go all around the curve, and this is the function of basically the length. Now I have to put the derivative inside, and we have already seen that we take the derivative of the first component times the second plus the second times the first. These are symmetric, so that's why we get these two here. And then we get here, and we're going to have to reverse the order here of derivatives. And instead of c derivative with respect to p and then t, we're going to reverse that. So it's a bit of calculus. And we get at the end this expression. So this is the expression that governs the change of length. And we're going to see an example in a second for different v's. We can do the same for area. We basically, instead of inner product, we take the outer product or the determinant. We have already seen that. We take basically the two vectors and we take the determinant of that matrix, and that computes area. We can also look at the change of basically curvature. And these are the equations. Again, I don't want to take too much time to do the whole derivation. They're not very hard. They appear in the book, for example, that I mentioned. But here we have the general formulas of the change of length, area, and curvature. This is actually a very interesting formula. It's basically, in some cases, it's called a reaction diffusion equation. It's the same type of equations that people use to model how basically patterns in the skin, patterns in the zebra are created. It has kind of a diffusion term and has kind of a shock term here for certain types of V. So let's just pick some examples and see what happens for different V's. For example, for V equal 1, the constant motion. So for the constant motion, we have V equal 1. And then the change of length, we put here v equal 1. So it's the integral all around the curve from 0 to L. Now, the integral of the curvature around a closed curve is always equal to 2 pi. That's basically a fundamental theorem in differential geometry. And that basically says that the length is changing at constant rate. the length is changing, so the derivative of the length is changing at constant length. And that, if you integrate that, it tells you when are you starting to see crazy things happening, as we are going to see in a second. So the time that things change, so you can either write it as a function of the initial length or as a function of time, you get it here. The area is basically, this was the general formula, but v is equal 1, and basically we have the integral from 0 to L of 1, that's L. So the area is changing proportional to the length. Now the length is changing, so this is not constant. This is constant, this is not constant. The area is changing proportional to the length. The curvature, this was the general formula, and we have then the derivative is equal to the curvature squared, because v is constant, so second derivative vanishes. Now you can solve this equation of derivative of curvature according to time equal curvature squared. You solve it and you get this equation. And look what happens here. This basically, the curvature blows. It becomes infinity when t is 1 over the curvature at the original curve. Remember, we say that things can create shocks. Basically, the waves are coming and boom, they collapse. And that's basically very high curvature, infinite curvature. When that happens, when this term is 0. When is that happening? When t is 1 over the initial curvature at this point. 1 over curvature is radius. So you know exactly when are you expecting a shock to happen. When are you expecting these waves from both sides to collapse? You go around your initial curve and you say, where do I have basically my curvature of this form? When is that going to happen? When is this curvature going to become infinity because it's collapsing from both sides? Oh, at time 1 over the curvature. The larger the curvature, the shorter the time it will become a shock. So if you have something which is already almost a corner very fast, it will become a shock. So from these equations, you understand the overall behavior of that. You can, of course, do that also for the curvature flow for the Euclidean case. And once again, you plug in the same equations. And in this case, this is the general formula of the area. Now the velocity now is curvature. So you integrate. Again, the integral of the curvature is constant. So you get that in the constant motion, the length was changing at constant rate. In the Euclidean motion, the area, in the Euclidean curvature motion, the area is changing at constant rate. And then I can solve for this and I can tell you exactly when is the curve collapsing. It's collapsing at time, which is the initial area divided by 2 pi. So you look at your initial area, you divide by 2 pi and say at this time, my whole curve will become a point. Remember, this motion collapses everything to a point, but all the way is smooth, in contrast with a constant motion. Here, everything is smooth. It just gets cleaner and cleaner, and it goes into a round point. At when? Exactly at this time. So that's why these formulas are important to understand how the length is changing, how the area is changing, or even how the curvature is changing. So those are really, really interesting properties. We can do the same for the affine case, and you get these formulas. There is no kind of very clean way to solve this type of integrals. So you just get these formulas. There is no constant, basically, things here, although you can make an interpretation of some of the things as constants, but let's just not discuss about that in this moment. So basically, we have properties of these motions. Now, one of the motions, so these are curvature motions, constant motions. The active contours we talk about basically are this type of deformations, nothing else than that. And let me just give you one example of active contours velocity. And when we learn in one of the next videos, calculus of variations, after that we're going to be able to derive this motion in a more formal way. But even now, I can write it down and explain it to you. So this is v. What we have here is v. So this equation looks very long, but it's nothing else than a deformation with a certain velocity in the normal direction. Now, what are the terms inside here? So this curve is basically going to deform with a certain velocity. Now, what are these terms? Here is the curvature. No problem, we know it. Here's the normal, here's the normal. What's g? G is, for example, it's a function that depends on the image, and for example, 1 over the gradient of the image. Now, why do we need this function? Let's say that this function was not here. Let's just leave aside this term for a second. Let's assume that this function was never here. So we have Ct equal k, kappa, curvature, collapses to a point. I don't want that. I want this red curve here basically to stop basically at the boundaries of the shapes. I don't want it to collapse to a point. So how do I do that? I make it stop at high gradients. So if g is proportional to 1 over the gradient of the image, then let's say that I have a very strong boundary. The gradient is very high. Let's assume it's infinity. And then g is 0. So the curvature is trying to collapse, but it gets multiplied by 0 and then stops. Say, hey, I cannot move anymore. I need to stop. There is no more velocity. And that's why you have this term here. Now, we never have ideal shapes. So this derivative of g, remember, g is 1 over derivative of the image, for example, the gradient, or any other type of function. You take another derivative of that to make that stopping term even stronger. Even when there are no perfect edges, that this will not be 0. You basically create a potential value by taking the second derivative. And of course, that doesn't have to be in the normal direction, so you have to project. We know that. Every time we have something that is not in the normal direction, we have to project it to the normal direction. So this is almost nothing else than curvature motion. So a simplified version of active contours is this. It's curvature motion in the normal direction multiplied by g. G is a function of your image. It's the one that tells stop when you get to very high gradients. And this second term just makes that stopping even stronger. So here it is. We saw active contours in the previous week, and now we have been talking about differential geometry, and we have been talking about curve motions and how things deform. Why? One of the reasons is to get to active contours. You're an expert now in differential geometry, and you're an expert now in curve evolution, curve deformation. So here it is. You could have designed this. If I give you 5 minutes to say, design a curve evolution motion that will get you active contours, many of you, most of you probably would have come with this solution. Just deform it smoothly, move towards the objects, but when you get to the objects, stop. And then people have done many different variations of this, but this is the underlying concept. You can add some constant motion that helps you to move faster, but be very careful. You can get shocks and you keep moving. So always you have to add terms that depend on the image, not just depend on the curve, depend on the image, so it makes you stop. And you can basically go wild and do very, very interesting things in curve evolution to get to active contours. Now remember, we know how to define these properties also for surfaces. So we could do that for surfaces as well. And basically, here is just an example of a surface. So these are snapshots of a surface that started basically from here, and it deformed, and it discovered inside there were basically 2 rings basically touching each other. And this motion is nothing else than the motion I just wrote for you, but now on surface domain. And here, this was an ideal object, white and black, so the gradient was very strong, and 1 of the over the gradient was very weak. So basically, when I did the surface evolution, ds dt equal, let's say, one of the curvatures, and can be the Gaussian, can be the mean. We could discuss more about that, what curvature exactly to put here. The normal direction, that will basically move, and then we have g, that basically will say, when you get to very, very high gradients, stop. So this is just an artificial example. We're going to see more examples of active contours later on, now that we're becoming experts in this curve evolution and differential geometry. This is just, as I say, snapshots of this evolution. So a lot of very interesting mathematical tools that give us active contours, which is one of the most useful techniques for doing image segmentation, as we have seen many examples last week, and as we're going to keep looking at more examples. So now we're experts on curve evolution, and I'm looking forward to seeing you in the next video, when we're going to keep learning, keep building the tools that will let us understand everything about these active contours and this type of deformation, as well as some of the material coming later on. Thank you very much, and see you in the next video.